Hi, I'm Dave Taylor, Product Manager of the Advanced Diagnostic Devices at Reichert Technologies. And today we're going to talk about the Reichert 7CR, non-contact tonometer with corneal response. We're going to talk about the influence of the cornea on the pressure measurement, and we're going to talk about our corneal compensated IOP measurement. Doctors have known for years that the cornea influences the accuracy of an IOP measurement. And over the past 10 or 15 years, it's come to light that the cornea has a much more substantial impact on the accuracy of the IOP measurement than previously appreciated. The ocular hypertension treatment study was a landmark study that brought the cornea's importance in glaucoma to light more than anything else. But it's important to note that the conclusion of the ocular hypertension treatment study was that the cornea is independently predictive of glaucoma risk. The ocular hypertension treatment study did not suggest that one should use central corneal thickness adjustment algorithms to improve the precision or accuracy of an IOP measurement. These IOP correction formulas that are based solely on central corneal thickness have actually been scientifically discredited, and glaucoma opinion leaders of the world are cautioning clinicians against using them. Let's take a look at some data that easily demonstrates this point. As you can see in this population data analysis, patients with thicker corneas tend to measure higher on Goldmann tonometry than patients with thinner corneas. However, the strength of this line is being predominated by one patient with a very thick cornea and two patients with very thin corneas. The vast majority of the patients in this population, in the middle, have very little relationship between the central corneal thickness and the Goldmann measured IOP. A statistical analysis on this data set shows you mathematically that when you attempt to apply this correction formula to individual patients, you have a 40% chance of adjusting the pressure in the wrong direction. And that's a very important point. Not adjusting the pressure by the wrong magnitude, but actually in the wrong direction. The fundamental problem is that thicker corneas only tend to measure higher on Goldmann. Thinner corneas only tend to measure lower on Goldmann on average. But when you take a population data conclusion and try to apply it to individual patients, it will not work in a large percentage of cases. The Reichert 7CR utilizes a dynamic bidirectional applanation system to quantify the biomechanical properties of the cornea. Corneal biomechanics is really what influences the accuracy of tonometry measurements. Let's take a look at how the system works. As the air jet impinges upon the cornea moves back towards applanation, and the system registers a signal peak upon the inward applanation. Then the cornea becomes indented, causing the air pulse to reduce in velocity. As the cornea returns to its original radius of curvature, it passes through a second applanation and registers the pressure a second time. As the cornea moves rapidly inward and outward under the air pulse, it develops a dynamic corneal resistance. There's a damping effect that takes place, and we quantify that effect by a measurement known as corneal hysteresis. And corneal hysteresis is the world's only indication of biomechanical properties of the cornea. It's that data that enables us to compensate the intraocular pressure based on these material characteristics of the cornea. The corneal compensated pressure measurement, IOPcc, is still a Goldmann correlated pressure measurement, and this is a very important point. If I were to give you a tonometer that was the most accurate tonometer in the world, but the average reading from that device was 25, no clinician would know what to do with that information. We went through painstaking efforts to make sure that the IOPcc measurement still agrees with Goldmann on average, but lacks the corneal contamination that plagues Goldmann tonometry. This publication by Medeiros and Weinreb looked at the effects of corneal thickness on Goldmann tonometry and 7CR measurements. As you can see, the Goldmann tonometer is significantly affected by central corneal thickness, and the IOPcc measurement is not. Even though the IOPcc measurement and the Goldmann measurement agree with each other on average, the IOPcc measurement is not dependent upon corneal thickness. Here we see data from 28 eyes pre and post LASIK. If you look at the Goldman measured IOP, it appears that after LASIK surgery, the measured pressure is approximately 4 millimeters lower than prior. However, the IOPcc measurement does not change after refractive surgery. While the IOPcc measurement agrees with Goldman on average, it has very little correlation with corneal thickness, it stays fairly constant after refractive surgery, and most importantly, it is better correlated with the status of glaucoma than Goldman tonometry itself is. So if a tonometer is supposed to help us diagnose and manage glaucoma, IOPcc does it better. This study looked at patients with asymmetric glaucoma progression, that is to say, one eye progressing much worse than the other eye in the same patient. The authors of the study looked at Goldman tonometry, central corneal thickness, spherical equivalent myopia, and IOPcc. And as you can see here, the IOPcc had the highest odds ratio of predicting the eye with the worst visual field progression. If a tonometer is supposed to help you decide which eye is at risk for glaucoma, IOPcc does it better than Goldman. Let's take a look at the measurement data presented on the screen of the Reichert 7CR. First and foremost, we have the IOPcc. This is the pressure measurement that we believe is more accurate, closer to the truer intraocular pressure. Below that, we have the Goldman correlated intraocular pressure, or IOPg. This is a more traditional Goldman correlated pressure measurement. The reason we show both measurements on the screen at the same time is because the IOPg is a little bit of a frame of reference. If a physician has been treating a patient or following a patient for a period of time, probably all of their data has been done with a Goldman tonometer or a tonometer designed to read like a Goldman. So this stake in the ground is an important reference point, and it's valuable to see the discrepancy between the IOPg and the IOPcc. Finally, at the bottom, we have what we call the waveform score. This is a sort of reliability index on a scale of 0 to 10. It helps the user know if the measurement taken was a quality measurement or not. On average and normalized, you should expect to see a 6 or 7 or above. On occasion, due to a lot of different variables, you might get a very low score. If the user sees a score below 6, I recommend taking an additional measurement to try and get a higher reliability. Here's a case example of a 53-year-old black male with glaucoma. As you can see by looking at the pattern deviation, there's significant visual field loss. The central corneal thickness in this patient is 598 and 582. The Goldman measured intraocular pressure is 15 millimeters of mercury. The patient is on IOP reduction medication. Looking at the 7CR measurements, we see the IOPg is in good agreement with Goldman at 15.5 and 15.0. However, the IOPcc is 19 and 18, significantly higher than the Goldman measured intraocular pressure. It's worthy of noting that the IOPcc measurement is in the opposite direction that would be suggested by a central corneal thickness adjustment algorithm. It's also worthy of noting that the intraocular pressure compensated for the cornea, IOPcc, is more in line with the actual status of this patient's glaucoma. Here's another case example. 57-year-old post-LASIK female came to the ophthalmologist complaining of blurry vision and pain in her right eye. The Goldman measured intraocular pressure is 15 millimeters of mercury. The IOPcc was 46 millimeters of mercury. Looking at the OCT image, you'll notice that there is a flap that has fluid trapped under it. This woman had an angled closure glaucoma attack, causing the pressure to spike severely. The cornea became edematous and water got trapped in the LASIK flap. The Goldman tonometer really didn't applanate the cornea in this case. It just smooshed some of that free water out of the way, and it looked like an applanation. However, the corneal compensated pressure measurement sees through that because it understands the properties of the cornea and gives you a truer pressure measurement. This is a great example to demonstrate the magnitude of error that can be possible with Goldman tonometry. The Reichert 7CR should not require routine maintenance. However, there are some basic cleaning tasks that you should advise your customers should be performed on a semi-regular basis, depending on patient volume. There are 4 optical surfaces that should be cleaned on a regular basis. There are 2 alignment windows here and here, and 2 optical windows inside here and here. Those windows are glass and they can be cleaned with alcohol. And clinicians can use a cotton swab lightly moistened with alcohol to clean the windows inside of these holes. You just want to make sure that there's no residue left, so they should be instructed to look inside with a pen light and make sure that there's no lint or any other residue on the lenses. Finally, the air tube itself should be cleaned as well. You can use a pipe cleaner, or you can use the wooden end of a common cotton swab. Slide it gently down the hole, slide it back out again to remove any contamination that may have gotten inside the air tube. And it's very important to remember to press the demo puff button on the machine 2 or 3 times after doing this to blow out any contamination. The Reichert 7CR is fast and convenient for the operator, comfortable and non-intimidating for the patient, and it's objective. There's no operator bias. And best of all, because it's non-contact, it's not necessary to anesthetize the patient's eye. Quite simply, the 7CR is the best tonometer for diagnosing and managing your glaucoma patients.